According to a popular misconception about recursion, the Fibonacci function cannot be computed efficiently without memoization. And today I want to debunk that myth by explaining the myth and then showing a linear recursive solution. Okay, so first let's understand the problem. So here we have a recursive Fibonacci function. It takes a number n and then computes the Fibonacci number n by basically switching over the n. The switch is called when in Kotlin. Okay, and here we have two base cases for our recursion. So Fibonacci of 0 is 0, Fibonacci of 1 is 1. That would be the first two numbers of the Fibonacci sequence. And otherwise, we have our recursive case where we call ourselves recursively with n-2 and n-1. Okay, and then the chain and the print line, I think, is best explained visually by example. So let's look at the output of the program. We want to calculate fib of 10. Okay, fib of 10 needs fib of 8 because that's 2 less. That needs fib of 6, fib of 4, fib of 2, fib of 0. 0 is one of the base cases, 1 is one of the base cases, and now we know what fib of 2 is. Okay. Then 4 doesn't only need 2, it also needs 3. That would be the second recursive call. 3 needs 1, but it also needs 2. So we calculate fib of 2 again, even though we just calculated it here. And if you look at the bulges of this curve, you will see fib of 2 is computed over and over and over again. For every possible numeric path from 10 to 2, whether you skip 2, that would be the first recursive call, or whether you skip just 1, that would be the second recursive call. And there's lots of them. If I scroll down, you can see all the bulges in that beautiful curve where we keep calculating Fibonacci of 2. Okay, so that doesn't sound terribly efficient. Why don't we remember Fibonacci of 2, Fibonacci of 3, and so on once we have computed that? The computer will not do that for us. We have to do that ourselves. And that is normally hailed as the solution to the problem. And it looks something like this. So here we have a cache. The cache is just a normal Java hash map where we have the base cases just as before. 0 is mapped to 0, 1 is mapped to 1. And then in our Fibonacci function, we ask the cache, do you already have a result for n? If so, it's just simply returned. Otherwise, this lambda will compute the n, and then it will be put into the cache. And this lambda is syntactically identical to the else block from before. So if you look here, this else block is exactly the same as the lambda function here. Okay, so how would that look? What output does that generate? You can see the output is much, much smaller. So once we compute Fibonacci of 2, we can reuse it. Here it's picked from the cache. And once we compute Fibonacci of 3, we can reuse it. Here it's picked from the cache. Then here Fibonacci of 4 was calculated, so we can reuse it from the cache. Fibonacci of 5 can be reused. Fibonacci of 6 was computed here. That can be reused, and so on. Okay, so every number is computed once, then reused once, and then never used again, because 2 is only needed by 4 and by 3. No other number directly depends on it. Okay, that works and gives us the correct output. And indeed, it's much faster. Okay, but if you look at the order how the cache is filled, so first we store the 2, then we store the 3, then the 4, then the 5, then the 6, 7, 8, 9, and 10, then the cache is simply filled from left to right. So this is the order of the computation. And that makes sense. We can't randomly fill this cache entry before we know these two cache entries. Right? So it has to be filled from left to right. So we could ask the question, what's the benefit of starting at 10 and then recursively descending to lower numbers and then recursively ascending to higher numbers again and then some zigzag pattern in between? Why don't we start at the left and then keep computing to the right? Shouldn't that be much simpler and more efficient? And that's the idea of the third solution. That's hopefully the solution that breaks the myth. So here we have two functions. We have our fib1 function, which simply delegates to the fib3 function and adds two additional arguments, basically the beginning of the Fibonacci sequence, the first two numbers. Okay, and then here we print that to the terminal. Maybe let's also start by observing the output to understand the example better. So we start with the n that we're interested in and the first two numbers of the Fibonacci sequence, and then we check whether n is 0. It clearly is not, so we decrement it by 1. That's why you see this countdown 10, 9, 8, 7, 6, 5, and so on. Okay, what happens with the other parameters? So the old b becomes the new a. For example, the old b13 becomes the new a13, and the old a plus b become the new b. For example, the old 8 plus 13 becomes the new b21. Okay, cool. So sooner or later we'll reach the case where n is 0, meaning there are no more steps to perform. We have reached the final result. The final result is then stored in A, and that's why we return that. But before we return that, we count the stack frames. In our case, we have 18 stack frames, and that sounds like quite a lot. Why are there so many stack frames in this simple program? I would have expected maybe a handful. So here we can see the entire stack. The last three entries are just some bootstrapping so that our own code gets a chance to run. Here we see the main function waits on line 6 for the fib1 call to finish, because once that call finishes, then we can print it to the terminal. Okay, and the fib1 function is stuck in line 10. That would be this call, because we have to wait for fib3 to return, so we can return it ourselves. Okay, and then in line 19, that would be this recursive call. Here we are stuck 10 times. That's because every time we counted down here in our example, we added another stack frame to the stack. Every function call normally adds another stack frame. Okay, so that doesn't sound like a good idea. What if n is much, much bigger? Let's say 10,000, and let's get rid of the debug output here, because otherwise the terminal output will slow down the process so much that we won't get to the interesting part, which should be a stack overflow error at about 10,000. Yeah, there we go, stack overflow error. So we can't put 10,000 additional stack frames onto our core stack. Sooner or later it simply blows up. Okay, do we really need all these additional stack frames? So why are we waiting for the result to return here only to return it ourselves? Wouldn't it be perfectly fine if we get rid of that additional stack frame? How could we do it instead? We could say, well, let's evaluate the arguments, then reassign them to the existing parameters, and then simply jump back to line 15, basically a go-to, if you will. And we can enable that optimization by writing tailrec in front of the function. And then that should work. So tailrec stands for tail recursion. A tail call is a call that once it finishes, it is simply also returned, so no additional computation happens, and that's why the optimization is legal. Now you can see the very large output, and if we look at the stack, now line 19, this function call doesn't appear anywhere on the stack anymore. So that's quite nice. Or another way to read it is, if you look at these two lines, that once this return statement is executed, we don't return to line 19, we immediately return to line 10. So this is the only call to fib3 that will be pending on the stack. Okay, and if you think about it even a bit more, this return statement will no longer exist in the bytecode. So here we have an invoke static followed by a return. And here, this will be compiled into a goto. That's basically how it works under the hood, but we have to enable that. Okay, cool. So now we have a linear recursive solution that doesn't even blow the stack, and I think that's quite nice. So tailrec is the magic source how you enable it in Kotlin. There are some other languages that also support that. For example, in Scala, that would be tailrec as an annotation instead of the keyword. And I would guess other modern languages also have that, maybe, I don't know, F# or Rust or Go. I honestly don't know. If you know, let me know in the comment section below.